And the other thing that we did today was what? Well, it's this whole 6, right? Which you're probably most nervous about, but again, we did enough of this. And when you see questions, which I'll probably do today, in fact, for you before the mock, you'll see that it's not a big deal if you know how to treat them. And we did this, but I don't think I asked questions yet. We're going to do these two the next time we have a morning HL, or the next 2 times. This is not in the syllabus. I still shake my head at that. And so this is what we did. 6.1.7. So it's basically a definition type of a assessment statement, but they're pretty involved if you let them be involved, as my notes do. And that's what I said in class, is that I wrote too much. And so one way of sifting through this, the best way of sifting through this, is to read through it. And I know it's taking me a while to scroll through it, but if you actually just read it and you don't multitask, you turn off your headphones and you get rid of your notifications and everything, and you just sit and read, it wouldn't take you more than 15 minutes to read this, but it wouldn't be a bad idea to do it that way. But the other way that I've set this up is that I've highlighted the stuff that is most important in blue. So I think it's the only time I ever did this, because there's just so much. And anyway, so I think I'll do the same thing that I did in class then, and not scroll up and down through this for this survey, because it's all there. It's all there for the taking. Rather, just talk to you with the assessment statement itself. So really importantly, scheduling and policies go together. Multitasking stands on its own. Virtual memory and paging go together. You can get this much from watching the video, you know, you're halfway there. And then interrupts and polling also go together. There are reasons why, as you're about to hear and see, without me scrolling down too much. Remember the context of this topic. This is about resource management, and 6.1.7 and the ones around it are about the operating system. The operating system is responsible for developing, well, I mean, it has developed. Any particular operating system will have developed, you know, over years of development, and literally thousands of people all together, maybe not all working on policies, but hundreds of people working on policies for the scheduling of RAM use and CPU use. So the old scrolling up and down through the activity monitor exercise, where you see there's a lot going on. And the CPU is working with all of these processes. Can I move that? Okay, there are lots and lots and lots of things that are continually happening. So the question is, with 8 cores in your CPU, who gets to use the CPU and when? And same thing with memory. Before I go away from this, I'll just quickly go to, I mean, it's the same thing. You know, all these things take memory. And who's to say who gets how much? Dreamweaver is just such a hog all over the place there. The OS, that's who. So the OS has policies, whether they are first come, first serve, or they're priority scheduling, or they're round robin. But there are policies. There are ways that things should be able to share the CPU and memory. And via the policies, scheduling is done. So the actual implementation of, okay, and it's a control unit, I never mentioned the control unit in class, but it's a control unit that says, you go here and get processed now. Part of you go over there and get processed now, and you guys wait in line, blah, 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 blah. So the actual scheduling is done by the control unit using the policies that are given to it by the operating system. And that's all I'll say. There's lots more below. Multitasking is just multitasking. It's a bunch of things either seeming to go at the same time, seeming to be happening at the same time, because obviously there's lots that is going on and it seems to be going on at the same time, right? But actually through time slicing, through scheduling done through policies, really there are only 8 things, if you have an 8-core processor, that are being done at the same time. Then you get into hyper-threading, and then you can talk about 16 things at the same time. But I think you get all that sort of stuff, and we've gone over it enough that I'll leave it at that. But the operating system comes into play. I guess that's the point before leaving it, is that for multitasking, true multitasking, or even pseudo-multitasking to work, you got to have several things involved. The hardware has to be able to be capable of it. The programming has to have been programmed to take advantage of it, like doing threads in Java, for example. And the operating system has to be capable of performing multitasking. So then, completely different, not completely different, but very different sub part of this assessive statement is virtual memory and paging. Virtual memory we've talked about before. That's where you pretend that part of the hard drive is RAM. You've run out of RAM, so you use virtual memory. And I've got 8 gigabytes. We did this before. I could do it again really quickly. That if I add up all the stuff that I've got, you've usually got tons of memory, and I do. Usually, not as much as I usually do, actually. But if I added up all these gigabytes, I'd quickly go over 8. I think you can just see that right now. 2, 3, 4, 5, 6, 7. I'm over 8 by the time I get to here, okay? And I only have 8 gigabytes of memory. If you want me to prove it to you, I go up here and I prove it that I've only got 8, I think, gigabytes of memory. So we must be using, and we are using, virtual memory. So on the hard drive, there is a swap file, or whatever you want to call it, which is a place that's fairly fast as places on hard drives go, and it can be used as virtual memory. But why it appears here is the operating system giving you the ability to use virtual memory via paging. And this is where I did show the diagram that paging is simply mapping physical memory or logical memory, not physical, logical memory to physical memory. So here's the RAM divided up into frames, and here's the application, or the really big file, or the program, or whatever. And it goes 1, 2, 3, 4 in order. The pages, the stuff that is read, should logically be ordered. Pixels on a picture are ordered, and lines in program are ordered. There's order. They can't be haphazardly placed throughout the process space. And so, but to continually rearrange stuff over in RAM, and there is more to this than I said in class, more than I'm going to say right now, but you can read through this and you'll get a better idea. It just makes sense. It is more efficient to simply have frames, and you just map each page to a frame, and the frames can be anywhere. They don't have to be contiguous. You don't have to go find a place in RAM that's got enough space for this one huge thing. You just use bits and pieces here and there. And really, without getting wound up on this one, that's enough. That it makes sense to have things, you have to have things ordered logically to work with them. But they don't have to be logically ordered in RAM, period. They don't have to be. So it makes sense to not worry about them being, I'm starting to repeat myself, so I'll leave it there. And then, but we didn't talk about virtual memory yet in relation to paging. So that's the way the page is going to work when you've got lots of RAM memory. But if you run out of RAM memory, paging comes to the rescue and just allows you to use the backing store or the secondary storage or the hard drive, whatever you want to call it. And so the pages are, once again, logically ordered, and they're mapped to either a RAM frame or a frame over in the virtual memory space of the backing storage, the hard drive. Which brings us to the last one, or the last pair, interrupts and polling. Interrupts have been introduced quite a bit and talked about quite a bit because we've done stacks. And it's a classic example of an interrupt being an urgent thing that needs to be attended to, so it sits on the top of the stack of things that need to be processed until it's handled. And if something more urgent than it, with higher priority, happens, then it gets sat on by that new interrupt. And so interrupts can keep on interrupting each other. But interrupts, the point that the notes get into here, and in comparison to polling, interrupts come from either software or they come from hardware. They come from a hard drive saying, oh, there's a problem, fix me, or from a printer saying, oh, there's a paper jam, fix me, no use continuing on printing the job because there's something that needs to be fixed. Okay, so interrupts come into the CPU from someplace, either hardware or software, and there's more on the software down below. And then polling is a nice thing to talk about here because polling is the CPU communicating. It's CPU directed. So from the CPU to all the different pieces of hardware that it deals with, basically it's just regularly checking. Are you okay? Are you okay? Are you okay? Are you okay? And all the different hardware parts just kind of sit there with their request and wait until they're polled. And it might not be a problem. There are other things that can be polled as well. Data can be polled, but you generally tend to think about polling more just being the CPU canvassing the hardware parts that it's responsible for, making sure that they're still online and that they're still functioning and that they're still okay. And I don't know how long this has been. It's probably been too long, but it certainly hasn't been 80 minutes. It's much better when you're in class, but if you're not in class, hopefully this helps. And if you were in class, this could have helped as well.